Hello class, this is Ms. Ayodeji with today's video on section 10.1 Taylor Polynomials. As you're watching the video, please remember to take good notes by writing down important information, vocabulary, formulas, equations, and examples. Feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what is occurring in the video. And at the conclusion of watching the video, write down a brief summary of what occurred in the video and submit that summary as well as a top question via the online whisk form the day before class. All right, let's begin. In order to start this section, before we started, we're actually going to review something that we've already done last semester. Last semester, we had nonlinear functions that we were able to approximate with a linear function, and this graph should look familiar. As you can see, we have a nonlinear function f of x. And as you can see for f of x, at a certain point a, we have a tangent line to the function f at a. And we use that tangent line to be our approximation of f only at x values that are close to a. Okay, so the closer x is to a, the better the tangent line approximation is, and the farther away it is, then the worse the tangent line approximation gets, as you see here. But the equation of this tangent line can be represented using this formula, if you guys recall. In this formula, if this is my f of x, then my tangent line approximation is the linear equation and looks like this, where a is the point that the function values share, both the function and the tangent line share, and x is a value close to a. So let's suppose a is equal to 0. So then we have a simpler expression, and we have the tangent line expression turning to this, or simply basically this. Well, actually, I tricked you guys. We really shouldn't have been calling it just a tangent line approximation. It's actually another name, and the other name for it is a Taylor polynomial of degree 1. Instead of just saying tangent approximation. They basically mean the same thing, but we're going to see why we use a Taylor polynomial of degree 1 instead of tangent line approximation. And in this case, our a is going to be 0, just to make things simpler while we introduce the topic. And the conditions hold in order for a function to have a Taylor polynomial degree 1 approximation about x near 0, we need to have the function value and the Taylor polynomial function value at that value a, in this case 0, is matches, and the first derivative of the function at a, or 0, matches the first derivative of the Taylor polynomial at 0. And this example shows you how those conditions hold. So let's look at an example and see how we would do that. They say now find the Taylor polynomial degree 1 for g of x is equal to cosine x, with x being near 0. So again, we have the same situation here. The only difference is instead of f, we have g. In order to come up with the Taylor polynomial of degree 1, we need to know what the function of g evaluated at 0 is, and we need to know what the first derivative of g at 0 is, and then we'll be finished, and we'll be able to come up with our Taylor polynomial. Well, first of all, because we have a cosine function and we look at our value is a is equal to 0, we know that the tangent line at that point for a equals 0 is a horizontal line and the slope is 0. So we have a very simple tangent line approximation because our f of 0 we know is 1, and our f prime of 0, i.e. the slope of the tangent line, is 0. So really, the tangent line approximation of g of x equals cosine x for x values near 0 is essentially 1. And that's only for x values near 0. And as you can see on the graph, this exactly is the tangent line. And as you can see, as x values get farther away from 0, the tangent line, or the Taylor polynomial, is no longer a really good estimate. So let's take a look at another, or a way to look at a better estimate, which is the quadratic approximation. Now, some of you are saying, we didn't do that, and we did not do quadratic approximations, but we can go ahead and do it now. In this case, we call this a Taylor polynomial of degree 2, and every quadratic function looks like this form, where you have a constant plus a constant times the x plus a constant times the x squared. Okay, so in order to come up with our Taylor polynomial degree 2 approximation, we need to figure out what our constants C0, C1, and C2 are. Well, because we're dealing with the second degree polynomial, we can easily determine, we can easily determine the first derivative of our Taylor polynomial and the second derivative of our Taylor polynomial using what we know about derivatives of polynomial functions. So if you recall, in order to be a Taylor approximation, we need the function value and the polynomial values to match at a equals 0, and also the first derivative values at a equals 0 to match, and the second derivative values for a equals 0 to match. And so we can use the fact that since g of x is cosine of x, then g prime of x is negative sine of x, and g double prime is negative cosine of x, then these function values should match when x is equal to 0. Okay? Well, if that's the case, then we have a lovely linear expression or solving systems of equations that we can use. In the interest of time, we're not going to go through and solve for each of the coefficients, but we end up using these two pieces of information, determining that C0 is 1, C1 is 0, and C2 is negative 1/2. So now we can plug in our values to our expression, and we have a Taylor polynomial to degree 2 approximation of our g of x cosine of x for x values near 0. And the final answer looks something like this. And this again only works for x values near 0. So let's take a look at the graph of that, because the question is, which is better, our P1, which was our linear approximation, or our P2, which is our quadratic approximation? Well, both approximations work for x values really close to 0, but as we get farther away from x values close from 0, then the second degree polynomial matches more values than the first degree polynomial does. Okay, so the idea is maybe if we want to get an even better approximation for more values of x, we should improve the degree of the Taylor polynomial that we're using. So let's take a look at the expression of a general degree 2 Taylor polynomial. And as you can see, it looks very familiar to a linear polynomial approximation up to this point, but because it's degree 2, then that means we've added an extra term, and that extra term looks like this. X squared is obvious, and f prime at 0 seems to be obvious, and then divided by 2 may not be obvious. Why do we divide by 2? In fact, the question is there a general form that we can do for any n-degree Taylor polynomial? And there is, and that makes life so much beautiful and more better. So if we have a function f and we want to approximate it with the Taylor polynomial of degree n, then we use this expression right here because this represents an n-degree polynomial. And the idea is, in order to figure out this more exactly, we need to know what the coefficients C0, C1, C2, all the way up to Cn are. And the way that you can figure this out is using the information that we know that the conditions are the function value at that point at x equals a must match for the Taylor polynomial for not only the function but also at the first derivative, the second derivative, all the way to the nth derivative. And the reason why they must match is because it wouldn't be a Taylor polynomial if it didn't. And to figure out the coefficients, we use this expression where f to the n represents the nth derivative of the function at the point a equals 0, all divided by n factorial. Now, some of you may be saying, where did the n factorial come from? And if we had more time in this video, I would show you, but your book does a good example of showing you how to get to it. So feel free to take a look at the book to see how that's done. So if that's the case, now I have a general form to figuring out the nth degree Taylor polynomial of a function for x values close to 0. And it looks essentially like this, where in order to determine the coefficients of our n-degree polynomial, we need to divide each term by its relative factorial. Okay, so you should definitely memorize this because this right here is very important. And if you see the terminology p sub n of x, that represents, again, the Taylor polynomial of degree n centered at x equals 0 or around x equals 0. So these x values have to be close to 0 if we're going to use this formula. All right. An example 3 in the book says, let's construct the 7th degree Taylor polynomial for the function f of x equals sine of x, or x near 0. And then it says later on to compare the value. We're not going to do that in the video, but you can on your own. So in this case, n is 7, so we need 7, well, we actually need 8 terms, f0, f prime, f double prime, all the way up to f to the 7th power. And because we're dealing with sine of x, we know the derivatives of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x, vice versa. So we list all the 7 derivatives from first derivative to 7th derivative of sine. And if you remember, the function values must match. So therefore, we know that f of 0, if all these values at 0 will give us these function values, okay? And then we can use that to build up our Taylor polynomial. And don't forget the n factorial on the bottom. So this is how it looks like. And when you simplify them all, you end up with our final expression for our Taylor approximation of degree 7 of this. And if you want to see if it's accurate or not, plug in pi of 3 for x and see if you get the same value for this as you would get if you were plugging pi of 3 to sine of x. All right, now the question is, how much of a better approximation of sine of x is our 7th degree polynomial? So let's take a look. And this is really nice. As you can see, it does it, just even though it's about 0, it does a good job all the way up to negative pi and pi. It seems to really match really close. So again, the higher the degree polynomial of Taylor, then the longer the approximation range is good. Okay. So I know we were talking about let a equals 0, but what if a is not 0? Let just a be any number. Well, of course, we can have a general term for that. But if I had started with the general term for a general a, it might have been more confusing. So I just let a be equal to 0. So let's see how that general form looks like. But before we do, let's review. We're talking about we started off with a tangent line at x equals a. So again, the function value and the tangent line value at a is the same. So it seems like this right here represents how far apart those values are. And of course, as x becomes a, then this goes to 0, so these values are the same. So really, this is considered like the correction, okay? In a sense, the correction. Oops. And so the first Taylor approximation looks like this, and we have a correction at 0 when x is equal to a. And so that means that we have correction values. All these terms are correction values in essence, okay? And so in order to determine the general form of the Taylor polynomial of degree n, we need again to know what our c values are, and our c values can be found using the general formula that we talked about, which is the nth derivative of the point at a divided by n factorial, okay? And that will work for every sense. Now, because a is not 0, then we also have to include x minus a as a factor instead of just times x. All right, so there you go. And we can do that for values where a equals 0 doesn't make sense. Like, for example, natural log at 0 does not exist, but natural log of 1 does exist. So in this case, a is 0. And if you recall, since we're talking about degree 4 polynomial, we need the first 4 derivatives of natural log of x. And then we need to evaluate them at a equals 0. And we evaluate them at a equals 0. I'm sorry, not a equals 0, a equals 1, we end up with all of these values that are going to be used for our coefficients as we saw up here. And so now it's just plugging stuff in, and as you can see, And then we simplify the expression and we end up with our final answer to being this form. And again, this works for x values near 1. If we take a look at the graphs for varying Taylor polynomials of degree, we can see that the higher the degree, the better, or the longer the approximation is good for. So in conclusion, things that I want you to remember about the importance of Taylor polynomials is that they give good approximations as long as the x values are near a. And the further away from a, they may or may not be good. But if you want to improve the range of how good the approximation is, the idea is to use a higher degree Taylor polynomial, because that means the larger the interval over which it fits the function closely is. All right, that's it. Thanks.